Hi guys, and welcome to today's video on using tree diagrams. Now, that does not mean I'm a horticulturalist. And yes, I looked that word up beforehand. Hey, I'm a maths teacher. Who does it English? Although I am English. Anyway, yes, I'm not dealing with trees. We're actually using tree diagrams in a mathematical sense. And it's really, really good to see you. As usual, now, if you are new to my channel, welcome. Where have you been all my life? Weird? I thought so too. Now, my channel is maths with a little bit of humour and a lot of understanding. So if you're new, do me a favour. There's a red arrow over there that you can hopefully click for me. And it says something like me, show me some support. Now, I don't get a penny from this. Why? Because I've got all of about 8 people watching. Ha! Heartbroken. And so it's just nice to know that you're watching and that I'm not sitting in a room talking to myself a little bit deluded. Although I suppose if you watch my videos, you'd probably see the journey of me going crazy over a period of time. But enough about me, and back to you. So what am I going to do today? Well, I'm looking at pretty much how to construct tree diagrams, how to interpret tree diagrams, how to find probabilities from tree diagrams, including the idea of replacement and no replacement, and I know I'll come to that in a moment, and how to tie this into the conditional probability we've been doing. Now, good news is, this is the last video in this series. The crowd goes crazy. Oh, jazz hands. So, if you haven't followed the one on unions and intersections and conditional probability, please go and have a look. They are actually some pretty good videos. But let's recap with some basic probability. And we know, because we've been doing this since year 7, to find the probability of something happen, generally speaking, we take the number of successes divided by the number of outcomes. So if we have a sample space of the numbers 1, 2, 3, 4, 5, and 6, for example, which could be the outcomes of an ordinary die, then I try to find the probability of having an even number. Well, how many even numbers are there? 3, so that's the number of successes because I'm counting an even number of success. 3 divided by the number of outcomes. And the great thing about a sample space there tells me how many outcomes there are. There are 6. And because we know in mathematics when you have a fraction, you must always cancel down. There is my final answer. Now, if you remember back again to year 7 and 8, these two rules here, we sort of lied to you, or we didn't give you the whole truth. And what we said was, if you want to find out the probability of something and the probability of something else happening, then you multiplied the two respective probabilities together. And if you wanted to find the probability of one thing happening or the probability of something else happening, you added the probabilities together. And that pretty much, what we didn't tell you was that was true for independent events. Now, what is an independent event? Well, if you imagine a coin toss that's going up and then coming back down again, and I don't have a coin, I'm really sorry, I'm poor. Yes, because I get no monetization from these videos, a whole new discussion. But as a coin goes up and then comes back down, we know that that coin is going to have two outcomes. It's going to either have a head or it's going to have a tail. And when I toss it again, I'm glad to say that this coin doesn't grow a personality and suddenly starts talking to itself and goes, oh, well, jolly good, sir. I got a head the last time, so it pretty much should be doing a tail this time. Just keep the thing 50-50. Because being a coin, we've done advanced mathematics. No, I don't know what that was all about. But that coin has no basis. It doesn't know what went on before. It doesn't really care what went on before. So we could have a head followed by a head. So that previous coin toss affected the next one in no way whatsoever. And that's what the definition of independent events is. Now, formalizing this using the language that we now have, when they are independent, then we know that the probability of A and B happening, this intersection of A and B, is effectively the probability of A times the probability of B. And that effectively is what you've been doing in year 7. And we know, again, using the language of union, that the probability of A union B, or the probability of getting them both A or B, would be the probability of A added to the probability of B. And believe it or not, those two rules there are the fundamental basis for tree diagrams. Now, I love tree diagrams. They are freaking awesome, as I say here. They have a start point, obviously. They look brilliant. They look like a tree sort of fallen over, which in Australia seems to be happening a lot at the moment with the wind and the rain we've got. And they have outcomes, they have events, they have pretty pictures. All we really need to know, as I say here, is whether the experiment is being done with replacement or without. And I'm going to do a simple example first of how to draw a tree diagram by looking at a simple coin toss. Now in this situation, as I just said a moment ago, a coin toss always has a start point, and I do a dot for my start point. And before I go any further, I think to myself, right, how many outcomes does a standard coin toss have? And so my sample space for coin toss is head or tail. And that's for one toss of the coin. So if I was to do this now and draw my two branches, The reason I'm drawing two branches is because there are two outcomes. I'm going to write head on one of the outcomes and tail on the other. Tick for an exam, that's good. And then I'm going to write down the probabilities of getting each of those. Well, the probability of getting a head on a standard coin is a half because there's one head out of two choices, and likewise for a tail. Now, what do you notice about those two branches? Oh, can I do that? Yeah, badly. If you take those two respective probabilities and add them together, they will always give you 1. And that doesn't matter if there's 1, 2, or 3, or 4, or 27, or 6. These values here on these branches must always add to 1 because there's no other way of getting those outcomes. Now, I normally draw a dotted line here because I'm saying, well, this is my first event or my first trial. I'm now going to look at, well, what would happen if I did my coin again? Well, if I get to the end of this branch here, then I've already received a head. Now, bearing in mind I just said, whether I've got a head before or not does not change what my coin's going to give me the next time. The great thing is I can now just draw another 2 lines off, another branch, as it were. Now, again, that branch just stands for, I've already got a head, what are the outcomes I could get next? And it just so happens my coin hasn't grown an extra head, it hasn't grown an extra tail, it hasn't suddenly decided it's going to land on the side or get stolen by pigeons, which is generally what my maths group thought would happen. And once again, my probability of getting a head and my probability of getting a tail is still a half and a half. Now, that was obviously assuming I got a head first. What happens if I got a tail first? Does it change? No. Again, I've got 2 branches. Why? Because although I've got a tail, my coin still has just a head and a tail. So there is my head, there is my tail, there is a half, and there is a half. Now, drawing a dotted line at the end here, I'm now interested in what that actually says. What is that tree diagram actually now showing me? Well, the first thing it's showing me what happens when I toss my coin twice. And so if I get to the end of this first section, this first branch here, then what I've actually got is a head followed by a head. Now, order in that situation is important. This second branch, I've got a head first followed by a tail. This branch, I've got a tail followed by a head. And this one here, I've got a tail followed by a tail. Now, that's brilliant to know, and we'll come back to that a little bit later on. But if I wanted to now work out my respective probabilities of getting these things, this is where I'm saying I've got a head and a head. So head, half, times a head, half is a quarter. And hopefully every one of you out there knows that when you multiply 2 fractions together, you multiply the tops together, you multiply the bottoms together. So what about a head followed by a tail? Well, the probability of getting a head was a half, times the probability of getting a tail, which was a half, which is also a quarter. Whoa! Tail followed by head, same thing. Just look at, follow the branches along and see what the individual probabilities were. Half times a half, which is a quarter. And hopefully it's no real surprise that once again, that's a half times a half, which is a quarter. Now, some important stuff to notice here. Firstly, this thing here now lists all of your possible outcomes from tossing a coin twice, otherwise known as your sample space for tossing the coin twice. So if I wanted to write my sample space for tossing the coin twice, I would have head, 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 tail, tail, head, and tail, tail, with the curly brackets because they're important. Tick, thank you very much. What do we notice about all of these values? Well, yes, you're going to say they're all a quarter. I get that. But add them all together. And what do they add together to make? 1. Fabulous number. And why is it 1? Because again, each of those fractions stands for a different outcome. And if we are listing all of my outcomes, then all of my fractions must add up to 1. As in, it's certain that 1 or all of those is going to happen. Or in fact, I suppose certain that all of them are going to happen. Now, we can use these to answer all sorts of probability questions, but I'm going to park that for 1 second. I've got 2 other examples coming up that we can answer some probability questions. So here's an example. Let's look at spherical objects in a bag. There are 6 blue marbles and 4 white marbles in a bag. Draw a tree diagram to show the possible outcomes and probabilities when 2 marbles are drawn. Great, so we've still got these 2 marbles are drawn thing with replacement. Right, now what that means is when I take a marble out and note its color, I put it back in the bag. What that means is my probabilities of choosing blue and white stay exactly the same. So just to remind myself, I've got 6 blue and I've got 4 white. And my sample space for one selection is either blue or white. So here is my start. And I've taken my first marble out. And because I know that it's got a choice of 2 colors, there is blue and there is white. Now I'm going to put my respective probabilities on. What was the probability of getting a blue marble? Well, there was 6 blue out of 10. So it's 6 out of 10. Now, I can automatically write that down as 4 out of 10. Why? Because those two branches must add to make 1. Now, obviously, I've got to be really careful that that value there, that first one I put down, is correct. Because otherwise, crash and burn, all sorts of horrible ideas. But I've done my first marble out of the bag. I'm now going to take my second marble out of the bag. So once again, doesn't matter what my first marble was. It just shows me that I've still got two choices on the second. I draw my dotted line here. Now you'll notice I've put both branches on at the same time. I can. I know that they're going to replicate each other. So I've got blue followed by white and blue followed by white. So that's the same. And once again, I've got 6/10 because my probabilities don't change because I'm putting the marbles back in. And I've drawn an awesome tree diagram. Is it finished yet? No. I now need to list my sample, my events, or what each of those branches stand for. So this is blue followed by blue, blue followed by white, white followed by blue, and white followed by white. And all I'm doing is reading those letters off of each of the branches as I zigzag through. They're like one-way streets. Working out each of the individual probabilities. So we've got blue, which was 6/10 times 6/10, which gave me 36 over 100. That was nice and easy. Now, don't cancel these down at this moment in time. My advice to you is leave them for checking purposes, and I'll explain what that means in a second. Right, blue is 6 over 10, followed by white, which is 4 over 10, which is 24 over 100, nearly. This one is 4 on 10 times 6 on 10, which is luckily 24 over 100. And white followed by white is 4 on 10 times 4 on 10, which is 16 over 100. And the crowd goes crazy. Or was that just me in my head? Yeah, I thought so too. And now the reason I said don't cancel these down is because I need to check that I've actually got this correct by adding all of those values together. So 36 and 24 gives me 40, 50, 60, 84, 100, 94, 100. And there we go, 100 out of 100. So I'm happy with that. That's literally done everything. And here is my sample space. If the question said to me, what was my sample space? I would be writing BB, BW, WB, WW. What I'm now going to do is effectively repeat the question, but I'm now going to do it that I actually don't replace the marbles. Here we go. So, same question. We don't need to write the blurb. But what you'll notice is at the bottom of my screen now, just above my head probably here, are some questions that I'm going to answer relating to that. So, I've still got the same thing. I've got 6 blue and I've got 4 white. My standard, my sample space for just one draw of a marble is still blue and white. And so I'm now ready to start. So here is my start. Yep, sound effects are free, blue and white. And because it's the first one, I've taken it out. There were 6 blue, so that's 6 over 10, and there were 4 white. Here is my dotted line just to make it clear to me that I'm doing another trial, and I'm ready to start again. Now, I've taken that marble, I've noted the color, and I've effectively thrown it away. Don't eat marbles, it's a bad idea. Really bad idea. But even though I've thrown one of those marbles away, how many choices of colors do I still have in those bags? Yes, hopefully I've still got 2 choices of colors. I've still got blue and white marbles. Doesn't matter if I've taken 1 blue out, there's still 5 left. If I've taken 1 white out, there's still 3 left. So I've still got 2 choices of colors. There is blue and there is white. There is blue and there is white. So now this is the interesting thing. Here, when I've got to here, I've taken 1 blue marble out. So there were 6, there's now 5 blue marbles left. So that's 5 on the top of there. But how many marbles did I have to choose from? Well, I started with 10, I took 1 out, so there must be 9. Knowing that, I can instantly write down 4 on 9 there because those 2 sections, those 2 branches have to add to 1. But just checking, even though I took a blue out, how many whites were there in the bag in the start? 4, so we should have 4 over 9. I'm happy with that. I'm now here, I've taken a white out. I've still got 9, I've now got 9 marbles left. And actually I'm going to write those in first because that's sort of the complicated part. And I'm going to say, right, I've taken a white marble out. How many blue marbles do I have in my bag still? I have 6. And in this situation, I would have 3 over 9. Do those 2 fractions add to make 1? Yes, they do. I'm very happy. So here we go. Dot, 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 dot. I'm not going to do any more because it said only 2 marbles are drawn. I'm now going to say, well, I've got blue, 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 white, blue, and white, white from my greatest Hull accent. Blue followed by blue is going to be 6 on 10 times 5 on 9. Now, obviously, we're not going to get divided by 100 in this situation because we took one of those marbles out. So 6 times 5 when I went to school was 30. And some would argue because I'm a teacher, I'd never actually left school. And blue followed by white is 6 on 10 times 4 on 9, which gives me 6, 12, 24 on 90. This one again is now 4 on 10 times 6 on 9, which gives me 24 on 90. And white followed by white would give me 4 on 10 times 3 on 9, which gives me 12 over 90. Now, again, let's just do my check to make sure that I've got all of my probabilities right. Add all those numbers together. 30 and 24 is 54. 54, 64, 74, 78, 88, 90. Thank you very much, 90. Tick, very happy. And here is my sample space for those 2 coin tosses. Now, let's go on. Drawing these tree diagrams, to be honest with you, is only going to be one part of whatever an exam asks you to do. Hint. What it will then ask you to do is find out various probabilities. And as you can see, down the bottom here, I've got 4 questions. Find the probability of a blue marble followed by a white marble. Now, in that situation, they are quite specific that they want an order to this thing. So all I've got to do is find BW, blue, white. Well, BW is here. And lo and behold, I would just write 24 over 90. Remember, that wouldn't be my final answer, though. I would need to cancel that down to 12 over 40, 12 over 45, which we cancel down again to, I'll leave that to you, too hard for my head. So there we go, I've done that one. 2 blue marbles. Okay, 2 blue marbles. Well, that's easy, we're just looking for blue, blue. So in that situation, 30 over 90, 1 over 3. What about this one? Exactly 1 white marble. Now that's awesome. Because in this situation, what it's saying is, just find out how many have 1 white marble. Well, in that situation, blue followed by white and white followed by blue would both fit that condition. So I now, in that situation, say I can have blue and white or white and blue. And if you remember, when we have or, we add them together. Yay! So in this situation, I would do 24 over 90 plus 24 on 90, which gives me a grand total of 48 on 90. And once again, I would cancel that down to make it a nicer form. Hi guys, I am MaffsGuru's Auto. That little voice in his head that went, oh, you forgot something. And yes, there is an important terminology for exams that maybe I should have mentioned, and here it is. The words at least. Now, generally speaking, we use at least 1. So, for example, at least 1 white. Now, if we look at that maths, what that means is 1 white or 2 whites in that example we were doing, which for the tree diagram would mean we would add 3 different probabilities together. But can you see the shortcut? Well, generally speaking, when you have at least 1 white, there's a quicker way of doing it, and that is to take no white, find the probability of no white, and take it away from 1. See what that does? It's so much quicker. Well, anyway, I'm done. You might see me in other videos when his little inner voice says he's messed up and forgotten something. Have a good day. A blue marble, given that a white marble has already been drawn. So I'm going to move this up for a moment. So I want the probability of a blue marble given that a white has already been drawn. Now, if we go back to our probability theory, we know we can re-express this as the probability of blue and white divided by the probability of a white marble being drawn. Right, okay. So blue and white. Where is blue and white? Well, that's this one here. So that's 24 over 90. Thank you very much. So that top fraction becomes 24 over 90 divided by a probability a white marble is drawn. Now, in that situation, it means that we can include 1 white or 2 white marbles. So the probability a white marble is drawn is given by, oh yes, 24 on 90 plus 24 on 90 plus 12 on 90, which in that situation is 24 and 24 is 48 plus 12 is 60, 60 on 90. And I'm going to leave it that way because it's going to make my life a bit easier. So 60 on 90. Now I divide by 90 there, cancels with the divide by 90 there, which gives me 24 on 60, which is 12 on 30, which is 6 on 15, which is 2 on 5, ladies and gentlemen. Now, I'm sure I could have done that quicker by dividing by 12, but sometimes doing it the quicker doesn't necessarily make it correct. You can make silly mistakes. See how this works? I should Coco. Now, ladies and gentlemen, as I say here, I'm going to a bit of a fast forward. I know probably if you're watching this, you are in year 10, but let's look into the future a bit with some methods 3 and 4. Ooh, exciting. Advanced maths. Now, we've already met conditional probability, and as I say here, we know that the formula, as I've just used there, is the probability of A that given that B is equal to the probability of A and B divided by the probability of B. Now, what happens if I rearrange that equation? Yes, I get the probability of A and B is equal to the probability of B times the probability that A happens given that B's already happened. And you're going to say, yeah, and? Okay, so looking at our diagram, cutting out all the stuff we did before, we know that for the first trial, we've got blue and white as our outcomes. So by the time we get to the end of here, I've got the probability of a blue happening, and here I've got the probability of a white happening. Yes, happy with that so far? Awesome. Now, I'm going to do another couple of things here. Happy? Okay. Now, what I want to say is I'm going to think of my tree diagram slightly differently. I just want to look at how I might describe this bit here. Well, actually, in that situation, assuming I've got a blue followed by a white and a blue followed by a white, that line that I've shaded in is the probability of getting a blue given that I've already got a blue. Ooh. And this white here would be the probability, just that line, of white given that blue. That one probability there. This one here would be the probability of blue given that I got a white already. And this one here would be a white given that I got a white already. Now, what's that got to do with the price of fish? Well, now look, what would I have done when I got to the end of each of these rows? I would have multiplied those together. So by the time I get to here, if I want to work out the probability of getting a blue followed by a blue, so if I wanted to find the probability of blue and blue, I would have done the probability of blue times the probability of blue given that blue has already happened. By the time we get to here, that would be the probability of white and blue, which would be the probability of blue times the probability of white given that blue has already happened. Do you see what I'm beginning to build up? This one here is the probability of white and blue again, all right? So maybe this one here I should have written as blue and white. It's not going to make any difference. We'll come to why in a second. Is equal to the probability of white multiplied by the probability of blue given that white has already happened. And this one here is the probability of white and white, which is the probability of white times by the probability of white given that white. And ladies and gentlemen, believe it or not, that's all this formula is here is actually saying. The probability of A and B happening is the probability of B times the probability of A given that B has already happened. That's just saying here I'm on my tree diagram, there's my probability of B, and here this is the probability of A happening given that B has already happened. And that's true because that line already says B has already happened. You use this in methods, believe it or not, 3 and 4, but actually you've got the total understanding now. Now, tree diagrams are really, really powerful. They're visual tools to help us view sample spaces and work out probabilities, yes? When we add all probabilities together at the end of those rows, it must, end of the column, it must be 1, as do the branches all add up to 1. Well, ladies and gentlemen, that is it for this lesson. Are we ready for my Twitter 45-second recap? I should Coco. Ladies and gentlemen, today we looked at tree diagrams. No, I am not a horticulturalist. Thankfully, tree diagrams and trees have nothing to do with each other than the fact they share branches. We looked at a recap of probability and we decided that actually back in year 7 we may have lied to you, or at least we talked about independent events without you knowing about them. And we said that when we do and, we times, and when we do or, we plus. And we constructed our first tree diagram. We looked at tossing coins and we looked at the ideas that when we multiply branches together and add branches together, we can look at this as a sample space and all of our various probabilities. We looked at examples where we did replacements, i.e. we put stuff back in bags and realized our probabilities didn't change. And we looked at an example where we didn't replace them and we had to make sure that our fractions took that into account. I looked at methods 3 and 4 and conditional probability before finishing with this recap. Breathe. And ladies and gentlemen, I think I am done for this video. Thank you so much for once again joining. It's always really good to have you here. Now, I asked you at the beginning, I'm going to ask you again, can you do me a favor and click that button and subscribe? What button? That one there. And if you haven't already, can you send a message out on Facebook and Instagram and Snapchat and whatever else, Twitter, and just say that I'm here. And the videos are free and reasonably good. Otherwise, there is a video loading for you over there for you to watch as well. All right, ladies and gentlemen, you have a good day, and I look forward to seeing you again soon. MaffsGuru, out.